joining the webinar today. Today's topic is Advanced Design Analysis on Noise, Vibration and Harshness, NVH, for electric machines. So as you know, noise and vibration is an important topic for electric machines. Competing requirements such as weight and cost reduction cause engineering challenges that, if unaddressed, can have an impact on customer satisfaction and product acceptance. So also there is an ever increasing need to improve the torque speeds of the motors. And with that comes issues like vibration and noise. So using the ANSYS suite of tools, we will provide engineering guidance on how to holistically address motor NVH. And please consider this multiphysics approach that we'll be showing in the following presentation as an example. Um, the overview this is the overview of today's presentation. We are going to go through, a quick overview of ANSYS capabilities on the multiphysics solutions for this application, and then we'll go into some of the ANSYS mechanical features which are relevant, like the modal analysis, harmonic acoustics. Also, how can we synthesize the sound, and also some stress analysis, which is an important part of NVH suite of analysis. So the question is, why to analyze the electric machines for noise? So from this survey which was done in 2011, it is evident that the electric motor gearbox noise is the third largest noise source for hybrid electric vehicles and electric vehicles. So the goal is to understand how we can model this noise. Of course, there are other noises like the wind noise, the road noise, and the ancillary system noise, other noise and vibration phenomenon, which need more intense analysis. We are going to be focusing primarily on the electric motor gearbox noise, uh, uh, which is uh, uh, which is emitted within the electric vehicle. So, as I mentioned, today's presentation will be primarily geared towards electric motor noise modeling and perception. So for that, we basically can solve this as a vibroacoustic problem in ANSYS Mechanical. We intend to capture the motor excitations from Maxwell and use that to finally arrive at user perception and noise. So we are going to solve for basically the electromagnetic analysis within ANSYS Maxwell. Uh, Map it to the structural components within the motor, then which cause vibration, and model the vibration, simulate the vibration, and then look at the acoustic response of because of that vibration. Then finally, how do we perceive that noise? We have some other tools in Optus that we are going to briefly go through. So a variety of simulations can be done within ANSYS for ANSYS Mechanical for performing any kind of structural worthiness of motor components. We can use all those systems in a standalone manner, or even combine them together to enable a multiphysics simulation. We can do a modal analysis to perform, free vibration or mode shape analysis to get the natural frequencies of the motor. We can then perform a harmonic analysis to get the response at each resonant frequency. We can also do stress analysis and within the structural suite of tools within ANSYS Mechanical, and then we can perform fatigue using either inbuilt mechanical fatigue tool within Mechanical, or Encode, which is a third-party tool but integrated into Workbench. So the overall NVH workflow is basically shown on this slide. So as you can see, we this is the workbench platform where we combine all the different physics. We have Maxwell 3D, which or 2D. So basically, the electromagnetic transient analysis can be done in either the 3D or 2D, and then we can map it to a 3D structural model. So this is the operation, the analysis B is where we convert the 2D to 3D, and then we put a, a, a 3D model with for the structural analysis. But we are going to be mapping the forces from a 2D Maxwell model to a 3D mechanical model. Now, the first step is to perform a modal analysis. Then we use the modal analysis to perform a harmonic response. And then we also do harmonic acoustic, uncoupled harmonic acoustic to look at the acoustic field. So these are the suite of tools: Maxwell, then modal and harmonic response analysis, and then finally harmonic acoustic analysis. So the first in this first system of analysis that we'll be performing is the modal analysis. As you can see, what we are looking for here is the eigenfrequencies of the structure, and we solve for this equation k minus m omega square times phi equal to 0 to calculate the required number of natural frequencies. We can look at the behavior of the structure with no load, and look at the different modes and the different frequencies and mode shapes corresponding to each of these frequencies. Um, then the next analysis in the process is basically harmonic analysis. So harmonic analysis is where we can use either these modes to calculate the response, or we can do a full harmonic analysis to basically solve for the equation of motion in the frequency domain, and solve for the response at each of these frequencies in the frequency range of interest. One important parameter which is typically of interest for this whole application is something called equivalent radiated power, or ERP. ERP is nothing but it estimates the radiated structure bone sound power from vibrating structure. So if you have a vibrating structure like this with a certain velocity Vn, we are trying to look at what is the structure bone noise which is radiated from the structure. So it is at the structure location, as you can see here. We are not looking at sound propagation, we are just looking at the sound generation. So this is basically a part which can be captured within the harmonic response or the structural harmonic response. So it is calculated using ERP is calculated using this formula here: half times density times the speed of sound times the radiation factor, and times integration over the surface, the structural surface for the normal velocity square. So this is basically the equation which is used in the structural analysis. You get to input these parameters and finally calculate the ERP value. So ERP can also be converted to equivalent radiated power level, ERPL, which is expressed as a logarithmic function, uh, where we where we divide the log of ERP by a reference sound power value, okay, to get the ERP level, which is in decibels. So once we do the harmonic response, structural response analysis, the next in the queue is harmonic acoustic analysis. So harmonic acoustic analysis is used to predict the noise propagation, once it's generated because of these structural vibrations. So acoustic analysis is performed to predict the noise level due to the force structural vibrations. This is the structure here. This is the computational, the acoustic domain. We could have symmetry planes for both these planes. Uh, then we can have a PML boundary condition to absorb the outgoing waves to represent a large domain so that there's no reflections. So all of this can be modeled within harmonic acoustics to basically look at the sound propagation which is being generated from the structural vibrating. So with respect to electric machines, what are the different things that need to be taken into account? What we see is the stator response. Calculating the stator response is very important, and that is affected by the cantilever teeth and the back iron, which is part of the stator. So looking at the modal analysis of both of them and looking at the different mode shapes is an important step in in the whole NVH analysis. Also, when the noise is propagated through the stator onto the enclosure, the housing and the brackets, it's important to also model them and account for the stiffness because of these housings and brackets. And so we'll be looking at some of the best practices for that. So as I mentioned, the stator response is very much dictated by the stator back iron and the teeth, which are similar to a cantilever beam, if you can imagine. So the stator back iron has a few simple ring modes, but it also has quite complicated modes as shown here. The radial and tangential forces, uh, which are uh, which occur in the because of the electromagnetic forces in the air gap between the rotor and the stator, those are transferred into the teeth, and the radial and the tangential forces cause deflection within the cantilever beam, changing the air gap. So it's important to model these deformations accurately and model the mode shapes which cause these deformations accurately in the simulation. So the goal is to have a good mesh in your model. So use a hex mesh whenever possible to improve the result with smallest mesh. We need to have at least two elements across the tooth and the back iron. Uh, with respect to the geometrical representation of the motor, so you can see that these motors come in different kinds of winding types. You can have form wound, stranded distributed, stranded concentrated. As far as the structural response is concerned, the goal is to accurately capture the mass inertia effects. So it doesn't matter what we are, how if we are modeling all of these windings in detail, because that leads to a lot of geometrical complexity. Instead of that, coming up with the simplest possible geometry representation, like capturing the actual length and end windings, uh, is good enough. You don't have to really go fine on the coarse meshing because you're not capturing the exact geometry. Also, using point mass wherever can help with accounting for the mass um, uh, inside the geometry. Uh, Now, with respect to the harmonic force calculation, as you can see, the main magnetic force is being calculated within Maxwell. Maxwell is the magnetic FEA modeling tool within ANSYS, where you solve for electromagnetic fields, which are converted to the force, and they are all done in the time domain. For electric machines, it's preferable to always start with basically a transient analysis within the electromagnetic analysis. But what we are converting it to a frequency domain because we are trying to map the forces to harmonic. So it's important to see how we can do the discrete Fourier transform on the time response to calculate the frequency response. So that part is done within Maxwell. Um, And when you in Maxwell, you can choose certain settings as to what on what parts you want to do the mapping and what kind of mapping you would like to do. So you can either do a object-based mapping or element-based mapping. Object-based mapping lets you choose the stator teeth on which you want to map, and the element-based mapping does the mapping on the entire stator. So these are the two pictures associated to the one shows the first, the top shows you the object-based mapping within mechanical. So once you set this in Maxwell and you link it in Workbench, these are the two kinds you can see. This is the object-based, which is mapped within within ANSYS mechanical, and this is basically the element-based mapping within mechanical. So this is basically the feature enable harmonic force calculation within Maxwell, which enables you to set up on which parts you want to do the mapping, and what kind of mapping you want to do. Within harmonic acoustic, what we do is we calculate the harmonic response and then connect the vibration analysis to harmonic acoustic analysis. So, which allows us to model the sound propagation uh, into the into the simulation region or the acoustic region. So you can see this is the acoustic region and this is the part emanating the sound or vibration. Um, in this, we basically have two approaches to model the outermost surface, or the absorption of the sound waves can be modeled using two different ways. One is the radiation boundary, and the second one is the perfectly matched layer, where you define an extra region called the PML region to define the region to absorb the sound waves when they are being emanated from the structure. Okay. Um, so how do we select the mesh size for this acoustic region? So the simple rule of thumb is that you calculate the minimum lambda or minimum wavelength based on the speed of sound through the medium. So if it's air, it's 340 meters per second, and the highest frequency that you want to capture. So if you do C divided by F max, that gives you the minimum lambda, and you want to have at least 6 to 12 elements through that wavelength. So that is how you would define the minimum mesh size for the acoustic domain. Now, how do you decide the maximum? So what the size of the domain should be, that depends upon the lambda max. So you basically take the C divided by F min, and that gives you the maximum lambda, and you want to make sure that you at least capture more than one lambda for the acoustic domain of domain size. So so once we go through some of the important best practices for the different physics that you have to solve, some of the results that you'll be interested in. So the modal and harmonic results are shown here. As you can see, we are calculating more than 30 modes here, and we are plotting the mode shape of a couple of modes here. We are looking at the mode shape corresponding to the 14th mode, which is 937 hertz, what is the mode shape corresponding to that, and again the mode shape corresponding to the 21st mode uh, uh, is being shown here. Now the response corresponding to this particular frequency is calculated within harmonic, as I mentioned, and here is where you can look at the deformation in the structure at 950 hertz and 1400 hertz respectively. So when we some more results that I had also mentioned before, the equivalent radiated power that can be calculated within the harmonic response, um, and we can sweep it over multiple frequencies, as you can see here. So we are sweeping from 100 to 2500 hertz and looking at the equivalent radiated power level, which is the logarithmic function, and we are plotting it. So all of this is at the decibel on the y-axis, and looking at what is the response at in the frequency sweep. Within harmonic acoustics, we can plot different kinds of results. We can definitely plot the the computational in the acoustic pressure, sound pressure level in the computational domain. We can also plot far field results like the sound pressure level A weighted. We can plot the far field pressures, phase, frequency band, sound pressure level, as shown here. So this shows you the far field SPL, uh, and this shows you the contour of that at a certain frequency. And this is basically the equivalent radiated power, the waterfall diagram that can also be plotted in the mechanical interface, in mechanical harmonic response interface. Now, once we have this ERP waterfall diagram, so how can we listen to it? Are there ways to listen to it? Because it's always good to be able to listen to all of this firsthand rather than just looking at these waterfall plots. So in 2018, ANSYS acquired Optis, which includes the sound dimension and perception tools. So using these tools, you can hear audio, you can monitor the psychoacoustics. Um, so if you're interested in doing that, you can use Optus VRX, sound dimension to do some analysis, psychoacoustic analysis on these noises. Um, you can also export this to a waveform within a harmonic response and just listen to them using a simple Windows media player. If you don't want to do any psychoacoustic analysis, if you just want to listen to it, it can be done by directly exporting to a waveform, and that's available in 2019 R2. So this interface that you're seeing is the sound dimension product within Optus, where you can listen to the sound based on the waterfall diagram. So when we are doing optimization, it's what we see is, it's good to have these results and be able to see what the response is because of certain magnetic excitations, magnetic forces, reluctance forces, which is caused within the electromagnet. We can, if we can, map them to a structure, look at the structural response and acoustic response, it's good. But with a lot of times we are trying to optimize our design. So sometimes it's not just good enough to just visualize the result, but we would like to optimize the various elements. So a typical design target would be, maybe designing this motor lighter, um, having low noise, so maybe minimize the sound pressure level at 1 meter distance from the motor casing, um, and in that process, what are the different parameters which are of interest, and how can we uh, how can we properly design based on these parameters. So in this optimization analysis that I'm going to show you, we are going to play with four parameters in Maxwell, which is one is the width of the slot opening. So this is the width of the slot opening, the height of the slot opening, which is this one, the q-axis flux path width on the rotor, this one, uh, and the thickness of the rotor magnetic bridge right here. So based on the past experience, we see that these are like some important parameters that could affect the overall force forces which are mapped on which are mapped onto the structure and which cause vibrations. So the goal is to minimize that. Um, so this is done using the optimization tool OptiSlang, and as you can see, OptiSlang is integrated into Workbench. It's a third-party tool, but we have an ANSYS flavor of it, and it's called ANSYS OptiSlang. You can install it, and you can simply use this along with the different physics, because it gets attached to the parameter set. So any parameters that you defined upstream get propagated into parameter set, and the optimization analysis can be associated to that. So what we see from OptiSlang is that we can perform like two important analysis. First is we want to know what parameters are important or critical to our design. So from this, it seems that if we look at, say, the different parameters, we are just plotting the two of them, because we see that out of those four, which, the total coefficient of prognosis or COP is 81%, and but most of them is contributed by these two parameters, which is the q-axis width and the flux bridge. So these are the two parameters which cover most of the percentage there, which affect the equivalent radiated power level and the torque. And you can see the torque is captured up to 98% using these parameters, which means that we have captured most of the parameters which will affect the two parameters. One is the equivalent radiated power level and the torque. So this kind of study can be very helpful, because it can help you narrow down your parameters. So you could have maybe hundreds of parameters to begin with, and then if you can narrow down to fewer, it can give you a great design insight as to what are the important parameters that you want to focus on for your design. Okay. The next step is basically performing a response surface optimization. So here we are is where we can define certain criteria or goals that we want the mean torque to be greater than we want to minimize the noise but maintain the mean torque to be greater than 235 Newton meters. So when we have certain criteria like that, we can do basically we can monitor multiple points on the response surface to come up with the best design point. So here what we see is the best design is the 19 design point, and it can help you get the goal that you're trying to achieve. So it's the mean torque is 235, the equivalent radiated power is 67. So this you're trying to minimize it. So this is the minimum equivalent radiated power level that we came up with this torque consideration. Also, the best design, the 19, has got these dimensions for the flux bridge and the q-axis. So it helps you identify what is the right design for the criteria that you want to meet. Uh, So in an ideal scenario where all components of the gearbox are rigid and the gear ratios are perfect with no misalignment between the gears, no noise would arise from the gearbox. However, in reality, gears, shafts, and bearings are flexible, and manufacturing tolerances do leave misalignments. The purpose of a gearbox is to transmit power either with a step up or a step down in rotational speed. So what we can do is we can have this sort of ANSYS motion or ANSYS rigid body dynamics. ANSYS motion is a more capable tool, because what it does is it's a high fidelity multi-body dynamics tool where you can model the gear train motion and get a better understanding of the gear train NVH. Of course, this is a different a different source of noise that I just have one slide on, just so that you're exposed to this particular feature within ANSYS motion, which can capture whine noise and rattle noise occurring inside the gearbox. But that's just so that you have it in mind. So let us know if you're interested in that. Also, I'm going to before I show you the demo, I would like to show you this case study. This was done by Ford, and these are existing customers, and they were willing to share this particular case study. So I would like to share this with you. Uh, so here the objective is clear that the motor design for the motor had to be changed for higher speed operation. Um, so which when based on these, we want to minimize the changes as much as possible to meet the higher speed, and if there are changes, we want to monitor the impact of those changes. So the need to determine the size of the bridges that can hold the magnet. So the bridges which hold the magnet, they are of the pockets are very important. So the goal was to look at how to design these pockets efficiently. So some of the important things that we have to keep in mind for designing these is that we have to meet the stress criteria. Uh, we have to maximize the torque. Um, uh, and so should be minimum torque reduction, uh, and evaluate the impact on the loss, the tooth forces, and demagnetization. So as you can see, it's a multi-physics problem here. We start using a CAD tool to generate the geometry, define different geometrical parameters which correspond to the which can be used to define the shape of the pocket. Then transfer that geometry to perform electromagnetic analysis and calculate the torque ripple. Uh, Also use the same geometry for doing structural FEM analysis to calculate the stresses within the pockets, and then use both of them for the multi-objective optimization analysis. So in this, there are two levels of analysis that were done. The first level was to make sure the average stress is stable, um, and it depends mainly on the width and the length of the bridge. So there were two parameters that were defined for level one. For level two, the max stress is very sensitive to the curvature of the magnetic pocket. So the goal was to evaluate the geometry of the curve. So whatever control points, or to define that particular spline curve, that was basically the parameter. So there were multiple parameters here to define the shape of this pocket, and in the first one it was just two parameters. So if you look at this, this is basically the level one analysis, where this is the two parameters, this one and this one. So these two were, these two and these two. So there are four parameters. And in level two, all of these were different parameters. So there are about 30 parameters to define the shape of the pocket. And uh, basically the optimization tool within Workbench was used to come up with the best design and perform level one and level two analysis. So finally, these were the results. As you can see, this was the original geometry with level one set of analysis. This was the shape of the pocket, and then finally the contour was further refined using level two parameters, and these were the final results. Um, so with that, I would like to get into the demo.